So this is Beyond Horizon TMUA mock paper. Beyond Horizon is a tutoring business website thing. The website is below. There's a team of guys doing it. They seem pretty cool. This paper is available on their website. Just click it. It's like under our resources, and you'll find it. It's not that hard. Anyway, you'll find the paper, and you can have a go at it, and then you can watch this video. People keep asking me for, where can I find more TMUA-like questions? Well, here you can find some more. Here's a whole paper of them, and apparently there are more papers to come. So yeah, thank you to all the people who bother to write these kind of questions, because I certainly can't be bothered to. One of the things that I would say about this paper in particular is stick with it. Don't just discard it after the first 5 questions because a couple of them are gross, like this one. Just keep going with it because the questions do end up being really good, particularly in the second half and towards the end. This question is fine aside from this notation just not being a really TMUA thing. These open brackets and stuff is just not something that you'd find. But it's okay because the rest of the question, the idea of the question is certainly TMUA-like. We're just saying which inputs can we not put into here and for which we'll get undefined f of x. Well, firstly, we can't divide by 0. So if that denominator is ever 0, then we have a problem. But also, we can't put anything negative or 0 into the log. So that's 2 conditions, right? And we'll check both. So the first one was making this denominator 0. We can't do that. So any x's that do that are going to obviously not work. Raise both sides to the power e here, obviously. E to the power 0 is 1. And solve this. You end up with this quadratic that's been hinted at in the question, of course. And so, yeah, we can't have x be either of those things. The answer is one of these 3 things here. Or I guess it could be e. But sure. And then we also can't put anything negative or 0 into the log. So we also have to have this thing here. Well, we need it positive, but I guess if I'm writing this, then I'm saying the values that I get in the end will be the ones that I can't have. So yeah, we solve that. It factorizes straight away, right, which is nice. And then of course it's a quadratic that's the right way up. We want to be in between the roots to be less than 0, so that's in between -1 and 3. So we can't be in between -1 and 3, and we also can't be these two values. That's this notation here. It's saying we can be anything down to -infinity and -1 not included. This open bracket means not including -1. A square bracket would mean including -1. And we can also be anything from 3 to infinity, of course not including 3 or infinity, I guess, and not those two things either that we found before. So yeah, that's the answer there, C. And yeah, nice question to start with. Another horrendous question here for question 2. They've introduced the floor function here, but they're cubing first, right? So we need to think about what this graph looks like. If you cube anything between 0 and 1, you get something between 0 and 1, which then floors down to 0. So that's just going to be 0 between 0 and 1. And then if you cube something between 1 and I guess the cube root of 2, then you'll end up with something between 1 and 2, which floors to 1. So there'll be a short space where you're equaling 1. And then, of course, if you do anything between like the cube root of 2 and whatever the next step is, you'll go up to 3. Sorry, you'll go up to 2. So I guess we're now up to whatever cubes to 2 is the end of this thing here. No, I said this one was the end, the cube of 2, didn't I? So what was this one? Yeah, no, this one is the cube. So this is 0, this is 1. This is the cube root of 2. So this one ends, I guess, at the cube root of 3, I guess. Sure. Because, yeah, and then the next one, things above the cube root of 3 will then floor down to 3. It will continue with steps like this, so 0, 1, 2, 3, 4, and so on. Now the thing is, it will happen exactly the same on the other side, except it won't because it goes down earlier. So for example, between 0 and -1, and when you cube that, you're between 0 and -1, negatives still cube to negatives, which floors all the way down to -1. So you end up with the same width of space, but down one section. And this one here, likewise, you end up with the same width from -1 to minus the cube root of 2, I guess. But it's flooring down to -2, right? And then the next bit will be flooring down to -3 and so on. So basically you have the same graph either side. I mean, the first thing I guess I could have said before was that the integral of t cubed between these numbers is 0 because of course it's symmetrical and just cancels each other out as an odd function. But this isn't quite an odd function because it's not quite symmetrical. I mean, there is symmetry here, right? The things do match, but they don't match perfectly, right? Like they're not in the right place. But what we can do is we can just sort of balance out the area. So for example, if we look at this one, which was flooring down to 1 here, and this one that's flooring down to -2, it's the same width from these two lines here, right? So the area, this area here, the one that's not squared, that cancels with this area here, I guess, right? The boxes are just the same size. So therefore, because it's going, the height is 1 and the width is whatever the width is, and likewise here. So therefore, those two areas will cancel, and you'll just be left with this area, which is just 1 down, and some distance across. Now, it's tempting to think that the sum difference across is important, but it's kind of not, because the same thing happens with the next strip, right? This area here cancels with all of this area, and you're left with this box, height 1. And again, the width of this box doesn't really matter too much, because that's going to happen over and over again. It happens here as well, of course. This, I mean, essentially you could think of these areas as cancelling as long as you get rid of this area here. So you would just end up with a massive rectangle width 100 across, because you're going down to minus 100. So you didn't need all the individual widths, because you know it just carries on until minus 100. All of the stripes do the same thing. They just cancel one area, or not one area, but one height, a box of one height getting smaller and smaller, all the way down to minus 100. And so the area here is just 100, but of course the integral area would be minus 100 because it's underneath the axis. And so the area there will be minus 100. Again, they probably wrote the two hardest questions, 1 and 2. So that's why I'm saying don't give up on the paper here, because it does get really good. It's just the first two questions were really, really gross. This is a much nicer question that's very TMUA-like. We see a mod function, we're going to sketch it. X plus 2 is obviously just a line like this. X squared minus 4 is obviously a quadratic that goes through at minus 4 down here. And then, of course, if you're modding the whole thing, you need it to always be positive. So it's going to come down here. It's not going to go underneath here because it needs to be positive. So it's going to reverse itself and go up here like this. And you end up with this picture. We want f of x, the red one, the modded one, to be less than g of x. So we're just looking for places where the red graph is lower down than or underneath the black graph. Well, that's clearly between here and here. We already said that this value, or we know this value is 2, right? Because it's just the roots of that one there. So, of course, the two solutions are between somewhere less than 2 and more than 2, and the only one that works here is this 1 and 3 answer here. So you could equate them and actually find it out, but this is the only answer that makes sense. So we'll select it and we'll move on. Really gorgeous question here. This is possibly my favourite question on the paper. What's the sum of the coefficients here? Super tempting to expand this out, but you really don't need to. It would be good practice. You can use some of the trinomial expansion I've talked about in previous videos. But don't, because if you just say you have a function in its normal polynomial form, where it's just a plus bx plus cx squared plus and so on, until whatever highest power you have. When you evaluate it at 1, that by definition gives you the sum of the coefficients, which is a really nice little trick, because of course all the x's just evaluate to 1 and then just go away, right, no matter what the power is. So a cheap way of finding the sum of coefficients is just to evaluate the function at 1. But of course you don't need to evaluate that function at 1 after doing the expansion and getting it like this. You can just evaluate it at 1 straight away, because of course it's not going to make a difference, right? So I don't need to expand this. I'm just going to evaluate it at 1 straight away, and whatever the answer is going to be the sum of the coefficients. This makes 10 cubed is 1,000, and you'll end up with the answer of 1,000. Just a really lovely question. Question 5 is if the three hardest questions in this paper are 1, 2, and 5, which is quite a demoralizing way of writing the paper, but I respect it. But yeah, this is a question where we're basically just going to have to draw stuff and hope for the best. And that's sine of x, that's cos of x. I did cos of x in a computer because I couldn't get PowerPoint to draw it for me very well, whereas I just about managed with sine of x. Now we need to draw, we're going to draw cos of sine of x, I guess, is the next one to draw. Now, we can just, all I'm going to do is I'm going to focus on the points 0, pi over 2, pi, 3 pi over 2, and 2 pi. That's the only bits I'm going to draw, and then I'm just going to connect the graphs in between. So, okay, well, what's cos of sine of 0? Well, sine of 0 is 0, cos of 0 is 1, so that gives you 1 there. What's sine of pi over 2? Well, we can see it's 1, and then cos of 1, we can see, well, cos of 1, well, now this value is pi over 2, which is a bit bigger than 1. So cos of 1 is somewhere over here. In fact, based on this graph, it is this line here. It's some number between 0 and 1, so it's somewhere down here. So that's cos of 1, just there. And then the next one would be pi. So sine of pi is 0, as we can see, and then cos of 0 is 1. So we go back up to 1 again. And the next one is at 3 pi over 2. Sine of 3 pi over 2 is minus 1. So then we're doing cos of minus 1. But cos of minus 1 is whatever cos of 1 was, because cos is an even function. So that's going to be the same place as cos of 1, so it's there. And then finally at 2 pi, sine of 2 pi is 0. And then we have, of course, that cos of 0 is again 1. So it's just a function that oscillates like this, up and down. And then we'll do the same thing for the next graph here. So for here, y equals sine of cos x. Same idea, evaluation at the same points at 0. Cos of x is 1. Cos of 0 is 1. Sine of 1 is, as we've discussed, similar to cos. Sine of 1, this is pi over 2, right, which is a bit bigger than 1. So sine of 1 is a bit lower than 1. So we'll just put it somewhere and say it's sine of 1. At pi over 2, cos of pi over 2 is 0, as we can see. So therefore, we're going to do sine of 0, which is, of course, 0, as we can see from the original sine graph. Next one is at pi. Cos of pi is -1. Sine of -1 is the opposite of the cos case. Sine of -1 is whatever sine of 1 was, but negative, because it's down here. So it's at sine of, it's at minus sine 1. Next would be 3 pi over 2. Cos of 3 pi over 2 is 0. Sine of 0 is 0. And then finally at 2 pi, cos of 2 pi is 1. So we're back at sine of 1 again. And that would be that one done. And I think a normal TMUA question would probably end there and ask you how many solutions those two graphs had. But this question continues, and you have to do the whole process again. So now we're going to do the same thing we just did. So we're going to evaluate at 0, sine of 0. Well, in fact, we can use this picture now, can't we? Cos of sine of x, cos of sine of 0 is 1. Sine of 1 is whatever sine of 1 is. And then at pi over 2, cos of sine of pi over 2 is cos 1, as we discussed. So this is just sine of cos 1, which is just some value down here, I guess. And then we'll keep going. It's going to be up here again, and then down, and up here again. It makes a very similar graph. So that's that. I didn't even bother putting in the line this time, or the curve. And then over here, same kind of idea, except this one is a bit more interesting, I guess. At 0, we're going to do cos of sine 1. Now, cos of sine 1, as we discussed, is somewhere between 0 and 1. So somewhere between 0 and 1, cos is just something between 0 and 1, right? You're inputting something between 0 and 1. You're getting something between 0 and 1. So that's just cos of sine of 1. And now here, at pi over 2, sine of cos of x is 0, but cos of 0 is 1. So we go back up to 1 all the way up to the top again. And then next one at minus sine 1. But remember, cos of a minus is the same as whatever cos of the plus was. So cos of minus sine 1 is the same as cos of sine 1. Cos is an even function, so it does that. And then we just go back and forth. Again, there's another 0, so we're back up at 1. And then there's another sine 1, so we're back where we were before. Now, we just got to notice here that sine of what the order these values go in. 1 is bigger than sine of 1, which is bigger than cos of sine of 1, which is bigger than sine of cos 1. And we can justify that. I'll leave it to you to justify that by looking at the graphs and which kind of direction and how they're rising and falling. And I think it becomes fairly clear that this is going to happen. So therefore, it actually doesn't even matter which is bigger between these two. All that you really need to say is that 1 is definitely bigger than sine 1, because sine 1 can't be bigger than 1, right? Sine maxes out at 1. And also, sine of 1 is bigger than cos sine 1, because cos, again, it's making the number smaller. When you input something, it's making the number smaller than it was. So we know that this number is here, and it doesn't really matter whether it's above or below this one, because what's going to happen is when this number goes there, or if I try and draw these graphs on top of each other, this one at 1 is way bigger than sine 1, so that's going up here somewhere. And the next one, this one down here, is down here, because again it's less than sine of 1, and the next one's up here, and the next one's down here. So if you imagine these graphs being drawn, this one's going up and down and up and down, and the black one's going down and up and down and up. But if you just look in this section, they swap over. So there must be an intersection somewhere in this section, because they're continuous, they're going to glance each other. And likewise here, they swap over, so that's one section here, one section there, because they swap over, one there, because they swap over again, and one there, because they swap over one final time. And you end up with 4 solutions. I think that's also kind of a ridiculous question to put in here, but also quite fun and quite good to do. So yeah. And this question here, a nice little trick. The 6x is what's annoying in this question. So what you're going to want to do is get rid of it. How do you get rid of a random x? Well, you could complete the square. So we just complete the square to end up with 2 square things. And now all we're looking for, these need to be integers, right? So how many integers can we think that square and sum to make 13? Well, 2 squared plus 3 squared, or any of the negative counterparts, and in any order. And that's going to be 2 choices, 2 choices, 2 choices, 2 choices, I guess. No, that's not how you do it, is it? There are 4 choices here, right? Plus, plus, minus, minus, plus, minus, minus, plus, and then another 4 choices here. You're going to get 8 choices in total. And yeah, just a trick to get rid of these singular terms, just to complete the square. You see that in TMUA a lot. Okay, so apparently this polynomial here is divisible by x squared plus 1. Now you could do polynomial division. I'm obviously not going to. Anyone who watches literally any of this channel knows that I'll just sit here and refuse to do polynomial division all day. I'm just going to write it like this, right? If this polynomial is divisible by x squared minus 1, that means it multiplies by something to make it, multiplies by x plus 1 to make itself, right? So this is just what this means. Now we can see clearly here that this has got to be a 1x, because x squared times a singular x makes x cubed, so there can't be any constant here aside from 1. But also, when we try and multiply this out, we see that 1 times alpha must equal c, so alpha must just be c. And from here, we can kind of just say, well, okay, think about expanding this out. You're going to get cx squared, and that's the only x squared term you're going to get from multiplying this out. So c must just be the same as a, and then you're going to get a 1x, which is just the x here, so b must be 1. and then we've already multiplied out to match C. So I think we can basically make C and A whatever we want, but they must be the same, and then B just must be 1. So if C is 1, you just get A as 1, and then B has to be 1. If C is 2, A is 2, and B is 1, and you end up with 10 things, because you can just go up to 10, because this means that you're allowed to choose numbers between 1 and 10, by the way. Also a notation that TMUA probably wouldn't use, but that's just what it means, and I think most people could work that out. So a nice question here, you've got 7 cards, each of a different colour, and 7 envelopes. You want exactly 4 of the cards to go into the envelopes the right colour. So what I'm going to do is I'm going to pick the 3 colours / cards to not match. That's just 7, choose 3. So now I've just got the 3 colours that I don't want matching. Let's say red, blue and yellow. They're the ones that aren't going to match. The greens and the blacks, they're in the right place. I haven't got any choices of where to put them. They're just going in their right places. I've now done 7, choose 3, just to choose the 3 colours that aren't going to match. Now, how many ways are there to make those red, yellow and blue, or whatever I said the first time? How many ways are there to make those actually not match? Well, you've got 3 of them. Let's say you're doing the first one. If that's a red envelope, you can't put the red card in here because then you'd suddenly have 5 cards matching. So you can put the other 2 colours in here, but not the red. So there's only 2 choices there. Now the next one, tempting to say there are 2 choices again, but there kind of aren't. Because let's say this is the blue one and you put the blue there. It's tempting to say, oh, well, you can put the yellow or the red here, but you can't, right? Because if you put the red here, then the yellow would have to go in the yellow one, and that wouldn't work. So it turns out there's only 1 choice here and then just 1 choice there, and it's just 2 ways of doing it. You can actually just list out the 2 ways. That's probably easier than trying to justify it like this. Just list out the only 2 ways you can do it. 2 factorial is, of course, just 2 anyway, and you end up with the answer of B. Question 9 is a nice question. We just start with what they give us. So if f of 1 is 2, we can just put that in there, and we can work out what f of 2 is. Very standard kind of iteration stuff here. We work that out. Then we can put that value in here to work out what f of 3 is. And we'll get this, and then we can put that value in here again to work out what f of 4 is. What you very quickly realise if you do a few more of these, which apparently I couldn't be bothered to do, is it just goes up by a half each time. And this is one of those questions where you kind of just need to put your pencil down and assume that it goes up by half each time. This is TMUA. You don't have time to prove that kind of nonsense. Just trust that in these kind of questions, if there's a pattern, there's a pattern, and you just run with it. So it goes up by a half each time, which means after 100 iterations, it's going to go up by 50, and it's going to go up to 52 for our answer. Cool, I'll leave it to you if you want to prove or logically justify why that's definitely going to work, which it is, but whatever. Okay, this question's kind of cool. What I did was I split out this fraction here to make this, and then I just did some fun substitutions. So I just said, well, let u equal a half x, which means du equals a half dx, and you can throw that result in here. And then I just said, well, let m equal u plus 2, and then dm equals du. You can throw that result in here. Oh, sorry, I should also say I'm changing the limits, right? When x is 2, a half x is 1 and u is 1, and when x is 0, a half times 0 is still 0. You can pull this 2 out. You know, when you times both sides here by 2, you get 2 du is dx. Replace that and you get the 2 there, which I'm then going to pull out, I think. And then change the limits again for this substitution. And this is the Taylor-Swift law of integration. It basically just says when you've got a definite integral, the variable is called a dummy variable or a Taylor variable, you can also call it. And it doesn't really matter what the variable is, the result is going to be the same. So if we've got m's here, that's the same as having x's there. So therefore, we've got the original integral is equal to 2c lots of the original integral. So therefore, c is a half to make 2c equal 1 and make the left-hand side equal the right-hand side. And that will be that done as well. A very simple, well, not simple, but very standard question here. Replace the cos squared with 1 minus sine squared. Write the whole thing in s's, of course, because you don't want to be messing around with writing out sine every time. Factorize out the s, and then either s is 0, which means sine of x is 0. In this interval, interestingly, sine of x only has one solution, right? Equals 0, because you can't have 0 or 2 pi. So that's only got one solution. And then, of course, 8s squared minus... Why is there a 6 here all of a sudden? Is that just terrible typing on my part? Why is this not a 5? It should be a 5, right? It's just a 5, and I just typed a 6. And I don't know why I did that. I'm really annoyed about that, but it's going to stay because we all make mistakes, you know? We all make them. And this 5 is just going to apparently turn into a 6. It's clearly not going to matter because should it be a 6? Minus 6x plus... No, it should be a minus 5, right? It should just be a minus 5. Anyway, this is kind of wrong, but it doesn't matter because the idea is, even if this was 5/8, you'd root it to get plus minus a thing, and you'd have 2 solutions from the positive one because you'd have some number, you know, the square root of 5 over 8 is some number in between 0 and 1. and so is minus, it's between 0 and -1, so you end up with 1, 2, 3, 4 solutions either way, and the answer is still 5. So yeah, apologies for that mistake there, but it doesn't actually matter to the answer. Anyway, next one, maximize this integral. So it's tempting to just integrate, put the a and b in, and then work out how to maximize it from there. Probably not the best way of doing this. What you probably want to do is think about what this graph looks like, and I don't know how many times I've said that in this paper, but I'm going to say it some more. Think about the graph. This graph, it's just a quadratic, right? You can solve it. It's not difficult to do. You can use formula if you want, which is apparently what I did, and you end up with this. That means that it factorizes. I couldn't be bothered to work out that. So you have solutions at -3 over 2.5, which means it's also upside down, right? Minus x squared. So it looks like this. To maximize the integral is the area. So to maximize the area across an integral, you're just going to want to integrate between the two roots. You don't want to go any further because then the integral will get negative areas and will lower the final answer with some cancelling. So you just want to integrate between the two roots. So essentially you just want to integrate this between the half and -3 over 2. So you just do that. You're very, very, very careful with all the numbers, and you eventually end up with 32 over 24, which I think is 4/3 once you divide everything by 8. But yeah, just be careful with your inputting of the numbers there. Great question here. We're going to draw another picture with an x at 0, 0 and the line y equals x. And well, just think, how are you going to make a circle tangent to this there? Well, you can obviously have a circle like this, or you can have a circle like this. That's about it. And then you look, well, which centers are these? Well, it's the one where you've got a positive negative and a negative positive. And they're definitely not ones because they're definitely not zeros. So it's going to be what? This one, because it's positive negative is the center, and then negative positive is now a center. So it's clearly going to be C. Great question, this. Just really nice. We have a sequence that goes maybe a plus d, a plus 2d. This is the first term, second term, third term, and so on. This is the formula for the sum. You need to know that in TMUA. You're not given it, so please go in knowing that piece of information. The nth term is just going to be, now this is the first, this is the second, this is the third. So the third term has 3 minus 1 as the coefficient of d. So the nth term is going to be a plus n minus 1d. And the nth term they give you is x. So we have x equals that. And likewise the nth term, which is a plus n minus 1d, is equal to y. Now none of these equations have a or d in them. So we need to get rid of a and d from these things. If we just do this one minus this one, we can clearly get rid of the a. And then we can, I think I rearrange this a little bit here because these minus d and plus d cancel. Of course, then rearrange for d. And then I think what I did was I put the d into this equation for x. So this d has just gone into there. And I think I've done the same thing for y. And then rearrange that a equals x minus this business, just rearranging this line. And then I did the same thing for y. I don't know whether this is the easiest way of doing it, so I did both steps in one there. So I put this value for d in there and then also rearranged for a, and you get up with this. It's basically the same thing, right? And then what I did was I put in these results into this formula with this n here being n plus n, because that's what they're asking for. Except this a, I'm going to break up into a plus a and use this version of a in one of them and this version of a in the other. The reason I'm doing that is because I tried not doing that and I couldn't make it look like any of these things. I needed an x and a y, and I only had an x at the time because I only bothered doing it for x. But then I realized if I just do it for y as well and split it out, I can get the x plus y that I need. There's probably easier ways of doing it, but that's kind of my logic. And yeah, I just put it all in the formula using, again, n becomes n plus n. That's just putting it all in. I don't think I've done anything between that line and that line. I think I've just written it out again. And yeah, then we do some simplifying. This term largely cancels with these two if you look closely enough. I'm not sure exactly how I demonstrated that. Break this n out and leave the other two alone. And then these two cancel. And then write this one with an extra minus 1 in it, only to add the 1 later, and then these two cancel, and you just end up with the x, the x, the y, and the other term, and which is answer number A here, I think. So yeah, a really nice question, actually. So question 15 then. I mean, this is, again, a really nice standard TMUA question. How do we make this quadratic always positive? Well, if we think about the graph, we need a positive quadratic. If it's an upside down quadratic, this is just never going to be true. It's not going to be the case that for all x, this is going to be greater than 0, because if it's upside down, for some values of x, it's going to be underneath the graph. So we need m to be positive. is the first thing I'll say. And we also need no roots. We want the graph to be above the x-axis the entire time. No roots, of course, is b squared minus 4ac less than 0. So a is m, b is minus 6m, and c is 5m plus 1. Just going to put that in there. Say we need it less than 0. We're going to calculate this. We're going to expand. Can factorize out the m eventually, divide by 4, I guess. And yeah, we'll get solutions that m is 0 or m is a quarter. We're less than 0, so we need to be in between those two things because it's a positive quadratic. And yeah, then we just need to say that this is the answer, except, of course, just a very tricky thing here. And maybe this is given away by A being very close to D, but not quite. Why has D got an equals sign here? Well, because if you consider the special case m equals 0, all these terms go away, and 1 is clearly bigger than 0, so we are allowed to have m equals 0, and so therefore D will be our answer to this question. Now for 16, we are going to draw another picture. It's super useful to know what root graphs look like, so I'll just talk you through it very quickly. In case you don't know, y squared equals x looks like this. Now, this is actually kind of, I like to think of it as actually two graphs stitched together, because when you square root this, you're going to get y is plus minus root x. And this top graph is the graph y equals plus root x, and the bottom graph is y equals minus root x. It's actually two graphs stitched together. And we only have the plus one here. So when we draw this, it's just going to be the positive part like this, except it's also just graph transformations shifted 6 to the left. So it's going to look like this here. This graph obviously is just y equals x, so it looks like this. We require x to be bigger than or equal to minus 6, because otherwise we're rooting a negative. And essentially we're just looking for when the curvy graph is above this graph, which clearly happens between this intersection and this minus 6. Beyond there, the curvy graph doesn't exist, so we're not allowed it. So it's definitely either C or E. But where is this intersection? Well, we can just set them equal to each other and solve, right? We can just square both sides and not worry about it. We can solve this. One of these two things is obviously not going to work, and that's the minus 2. The squaring both sides created a fake solution, but that's fine. So the 3 is the one we care about, and it's between 3 and minus 6, and that'll be our answer there. 17 then. Again, this has been, I think, an exact question in TMUA at some point. Don't ask me which paper. There are more intelligent ways of doing this, but I decided to use the quadratic formula, which is just this. And then when I have both solutions, which is this one and this one, I'm just going to say, well, one of them minus the other one is 1/6. That's what the difference between them means. So just this minus this equals a sixth. And then, of course, the minus alpha over 12 bits will just cancel, because one of them is negative and one of them is positive. So you just end up with the roots over 12 equals a sixth, and then of course you can just, well, two lots, because it's plus, minus, minus another, so it's plus. Times by 12, I guess, divide by 2, very clearly the alpha is plus or minus 5 to make that work. Except it can't be minus 5, because alpha is a positive number. So therefore that. Now question 18, I just said that x, y, and z, we can just pretend are all equal, because they're all, firstly, they're all symmetrical within the question. And also, because they're all positive and things, I just said that we can kind of, without loss of generality, just pretend they're all the same, which leads to this. Like, think about it in terms of, like, if you just tried to make one smaller, there's no reason for you to pick that particular one. You may as well make a different one smaller, and you'd essentially just have to then do the same thing to all of them. That was kind of my logic, and I don't see any other way around this problem. People can probably explain it to me better than this in the comments. But essentially, if you just let them all equal each other, you'll end up with this. And if you just call that the function, of course, to find its least value, you can just differentiate it, solve it for 0 by timesing by x to the power 3 over 2 at some point, get x equals 1, and then just put x equals 1 to here, and you'll get 6, and that'll be our least value. Probably should have checked that's not the biggest value you can get, but of course, I couldn't be bothered. So the answer I'm just going to go with is B. You can probably tell I was losing. It's at the end of the paper. I was getting tired, so I was playing fairly fast and loose with this at this point. Anyway, pessimistic. How I feel about this, how this YouTube video performs in the algorithm. Pessimistic is going to be rearranged such that you can have no two s's, no two i's, and s and I not together. This question is really hard until you realise that there's a lot of repeated things in those s's and i's. And if you're not allowed the s's next to each other, or the i's next to each other, or the s's next to any i's, essentially you've just got to alternate between something that's an S or an I, and then one of the consonants that's not repeated, so the the P, E, M, S, or C. Sorry, not S, T or C. And then an S and I again, then one of those non-repeating ones, then S and I, and so on. And this is the only way you can make it work. So it goes S/I, whichever one you want, followed by one of the singular ones, followed by an S or an I, and so on. And you can kind of now just pretend this is two questions. You've got all these non-repeating ones, the P and the M and so on, which can just go here, 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 here. There's just 5 factorial ways of doing that. And then how many ways are there to arrange the S and the I's? Well, again, just get rid of these ones in your head and just say, well, it's a 6-letter word with 3 repeating S's and 3 repeating I's. So that's 6 factorial over 3 factorial, 3 factorial. I'll link a video in the description below if that made no sense to you. It's just a bit of theory about, you know, how many ways there are to arrange stuff. I'll put a video in for that bit. From here, you can just calculate, right? 3 factorial is 6. That cancels the 6 from here to leave you 5 factorial over 3 factorial. But of course, the 3 factorial cancels with the 3, 2, and 1 in the 5 factorial, so that's just 5 times 4. So it's 5 times 4, which is 20, times 5 factorial, which is 120, and you end up with 2,400 as your answer. Question 20, the most difficult thing about question 20 is that it is the 20th question, so you're already tired. But also, it's been written in a way, the hardest thing about this question is understanding what the hell it's talking about with all these cones. This is what went up on my board. This is, for every other question in this paper, I just did the question in PowerPoint. I didn't bother writing anything in any workbook or anything like that. But for this question, I just had to get the board out and just do it there. So yeah, the video around here, you can make sense of that. Except not really, let's just do it properly. So firstly, we need this formula, which I had to check with Mr. Winfield next to me because I couldn't remember it at the time. By the way, we were in a whole staff meeting when I was doing this. Probably shouldn't say that on the record, but this is what I was doing. Anyway, we've got 3 and 5 here. This is the first cone they're talking about. It's cut off, so its top circle is radius 1.5 like this. Now, if that's 1.5 across, because of scale factor of half, obviously the height is now 2.5 rather than 5. And if we call this frustrum A, we can work out its volume by just doing the original volume, take away the cone that we removed. So the original volume is just, of course, a third times pi times 3 squared times 5. And then the cone we removed, which is this bit, the cone we removed is a third times pi times 3 over 2 squared, the new radius, times that height that's missing, which is, again, 5 over 2, because it's the same as 2.5 up here. So you do some maths, you work out that this is this, and that's the volume of the frustrum A, so we'll leave that there. And now, what the hell does it mean when a cone is placed vertically inside A? This cone is bigger than A, so how do you put it inside of it? Well, you turn it upside down and put it down like this, which took a few attempts to draw. And then even more attempts to draw into PowerPoint, so that it looks in any way accurate. Anyway, this is cone B, it looks like this. And yeah, we can verify that this pointy bit doesn't go all the way to the bottom by just quickly working out the height of this little cone here, by doing 1.5 over 5 times 6. 1.5 over 5, of course, is just the fraction of this cone that is the whole thing, and then just times by 6 to get the new height. You get this, because of course this is 3 over 2 over 5 is 3 over 10, times 6 is 18 over 10, which is 9 over 5. And now I'm going to work out, if this is frustrum B, I'm going to work out the volume of that by doing the same thing with A, which is big cone, take away little cone. I'll leave you to verify that this is all correct. It took a while, just making fractions match and so on. And now, if we add A and B together, we're going to get the full volume of this frustrum plus this frustrum, which is just the whole volume of the thing. Except that's not actually what they want. What they want is not the overlapping area either. It's the portion of the cone excluding the part inside B, which is this part here. So we want to get rid of this little cone, so we take our final answer here, and we get rid of another copy of this little cone like we did before. You do some maths. Again, this is all non-calc, so it's not that easy, but it is what it is. And you eventually end up with answer C. Thank you so much for the guys from Beyond Horizon for making that. Again, you can check them out in the link below for tutoring and for papers and for stuff that they'll write. I'm sure I'll do some more of them as well. But yeah, thanks for watching.